Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at Chapter 8, which is modeling phase equilibrium for pure components. And we've been looking at the Clausius-Clapeyron equation, which is estimated from the Clapeyron equation by assuming that the gas is close enough to being an ideal gas, that the liquid phase is much smaller, in volume than the vapor phase, and that the heat of vaporization is more or less constant in this region where we have two phases. We want to now develop what's called the shortcut equation. So you can get rid of the heat of vaporization by introducing the Pitzer acentric factor. Remember, it's defined as omega equals -1 minus log base 10 of PR at saturation when TR is 0.7. If we go back and use the Clapeyron equation with this as our fixed point, then we can substitute this in, okay? So the critical point is 0.1. We're going to do this in terms of reduced pressure. PR sat over PC is negative delta H of vaporization over R delta Z times 1 over T2 minus 1 over TC. Okay? But T2 will be TR times TC. And so therefore, that grouping over there is log of PR saturated is negative delta H vaporization over RTC times delta Z times 1 over TR minus 1. You say, wait a minute, you haven't gotten rid of delta H vaporization yet? Don't worry. Okay, now the next thing I want to do is let's get rid of that log base 10. So natural log is log base 10 of x over log base 10 of e. And so I can log of PR sat is negative log base 10 of e times delta H of vaporization over RTC delta ZLV times 1 over TR minus 1. But now this is starting to look a little bit like my Pitzer acentric factor. If I rearrange that, log of PR saturation when TR is 0.7 is -1 plus omega. And so if I set TR equal to 0.7, I get that omega plus 1 is equal to, well, that delta H vaporization times the log base 10 of E over RTC times delta Z LV times 1 over 0.7 minus 1. Which is 3/7. Now combine these equations and I can eliminate delta H of vaporization. I end up with log of PR sat, now this is log base 10, is equal to 7/3 omega plus 1 times 1 minus 1 over TR. No heat of vaporization, I just need to have the acentric factor. So what if we went through and did this calculation? And we'll look at it for water because we've got lots of data for water so we can check and verify. So if we use the known vapor pressure of water at 20 degrees and the known heat of vaporization of water, the vapor pressure of water at other temperatures can be calculated, right? So in this example from the book, they did 0 to 400 degrees using Clausius-Clapeyron with the heat of vaporization. They then did this using omega and the critical point of water to calculate the vapor pressure using the shortcut equation. Okay, now we're not doing this calculation. I mean, you could if you wanted to, but we'll just look at their results. So, okay, this is the low. Now remember, they went up to 400. So between 0 and 50, what you see here is that the shortcut equation gave these results. Clausius-Clapeyron gave these results. The actual answers are those black dots. So at these low temperatures, Clausius-Clapeyron was awesome. Shortcut prediction, a little high. Wouldn't really trust it there. So for low temperatures, Clausius-Clapeyron is an awesome choice. But as the temperature increases, so now they're looking at temperatures up to 120. When you are at this scale, you don't really notice the problems with the shortcut method. But what you do see is that as the temperature increases, the Clausius-Clapeyron starts pulling away and it becomes high, whereas the shortcut method does a pretty good job. So as the temperature increases, the shortcut method is winning. And when we go to the very high temperatures, 200, 300, 400, look at the Clausius-Clapeyron. That's dreadful. Shortcut equation is really nailing it. So the lesson here is that low temperatures, where you are close to those ideal gas conditions, the Clausius-Clapeyron is actually going to do an awesome job. But as you get further away from that and closer to that TR equals 0.7 condition, the shortcut equation is really superior. So that concludes this lesson. We're going to come back and continue looking at these and other methods of calculating vapor pressure in our next lesson. Thank you very much for your time.